Good morning and good afternoon. So I'm going to start the FRQ series for the AP physics exam, basically for the 2026. So in this series, I'm going to continue with the multiple of the FRQ questions that we are going to be doing that one. Thank you to be here. So please subscribe to the YouTube channel. It's free for you, but it's very valuable for us. So to continue with this FRQ series, so that you can, as I upload that, you will get the next series of the FRQ questions are. Thank you. So let's come to the screen. So we have the first question is the student has the cart of the mass MC and the block of the mass MC by 5. And as you can see it here, so these are the official past papers, by the way. So on which that we are working upon, you will get on the website. I will upload the questions also for you as a separate link for that. In the description, you will get that one. So the question is, a student has a cart of the mass of the MC and there is a block of the, that is 1/5 of the MC. And as you see in the figure, so at the time t is equal to 0, the cart, the right side, it is moving to the right side with the velocity of the VC. And at the t is equal to t1, there is a one block from the top that is placed over there. T is equal to t3, so they are as they are start moving combinedly. So it gets stick together basically. So if you know the concept of the this is some kind of the inelastic collision when the two objects as they collide and they stick together. This is an inelastic collision. The first question is that we have it is on the axis shown in the figure 2. Sketch the graph for the magnitude of the px. Means the px is the momentum. So the x component of the momentum of the block and the system as the function of the time. So if you see it carefully, uh, so this is the block that the MC, the block we have the cart. On that you are going to be put the some kind of the block. As you put the mass on that, before the cart has some kind of the momentum. As you put it over there, so the momentum is it, you have to draw the graph for that as is equal to t is equal to t1 as you put into that. So what the graph will look like. So basically, the momentum will increase, decrease as you have it. What do you think about that? So now the thing is, so as you know, the momentum conservation concept is, so the momentum is always conserved when. So when the external force that is going to be act at 0. So let's look into that. So if you have the net force is most of the students say like this Newton's second law. So the what is that Newton's second law? Net force, the overall the forces that are acting on the system is equal to mass time acceleration. That everyone know that. So I'm going to substitute that. What is acceleration? Acceleration is the rate of the change of the velocity that we have it. So the change in the velocity that way. Now let me multiply that. So let me write it final and initial velocity. Final velocity, initial velocity, final initial divided with the delta t. I'm writing that one only. So if you see it carefully, that is mass into velocity. What is that? Is quantity is the momentum that we have it. Momentum is mass over velocity. Mass into velocity, that is the final momentum that we have it minus initial momentum that we have it and divided by this. So this is the net force that is come out to be. So right now, the Newton's second law, that is the original statement made by the Newton, that he said that the net force, that is the rate of the change of the momentum. So it is the same thing if you see it carefully. F is equal to ma. I just rearrange the few of the things. I substitute a few of the values, and then I get a net force is equal to rate of change of momentum. So how fastly the momentum is being changed, that is the net force that is going to be act. Or just see, interestingly, so if there is no external force, so now I'm going to write it. This is external force is the rate of change of momentum. So if net force is 0, that is, it means that the change in the momentum have to be rate of change of the momentum is 0. If this is 0, it means that the numerator have to be 0. So then the change in the momentum have to be 0. So, and the momentum is by the unit is kg meter per second. And this is the final momentum minus initial momentum. So let me make it small. Final momentum, initial momentum have to be 0. So it means that the final momentum and initial momentum of the system have to be uh, conserved. It means the momentum is conserved. So the final momentum is equal to initial momentum. And because remember it, momentum is a vector quantity. It means that if we have the two directions, means the momentum, initial momentum in the x direction have to be equal to the initial momentum in the uh, uh, final. And in the same way in the y direction, we always talk about the two maximum directions only in our syllabus. So we have the final momentum in the y direction also have to be, means I mean to say that you can convert the momentum separately in the x direction, the y directions, that you can convert that one. So if you look at this carefully, what the result that is come out to be, if external force is 0 on the system, then the momentum is conserved. So right now, what doing by external force? Now, external force is just when I'm doing the some kind of the collision. Right now, I am applying the force on the both the pen so that they collide. So this is my, I'm applying the force. This is external force. But if I leave that one and then they collide, so let's suppose on the table, suppose that I have this one and this one, they collide together. So if I leave this one, they collide together. Right now, the normal force that the book is applying on this pen or this lens card. So normal force is balanced by the mg force. So basically, there is no external force as it collided. So this is external force on the system is 0. In the same way, when something is moving in this cart, there is a cart is moving and something is put it over there. So this is if I take the pen and my notebook as a system. So there is no external force that is acting right now on the system. The point is, if there is no external force that is acting on the system, so the momentum is conserved. So you can apply the conservation of the momentum up to the T1, whatever that the momentum is, uh, that the momentum will remain the same throughout that one. And after that, also, I'm just saying that as it strike together or is stick together, the block and the cart get stick together, still the momentum remain the same. So the it always a straight line. Now, in the next part of the question, you had to drive it also. So drive an expression for the final velocity of the block of the cart of the system after the time t is equal to t2 in the term of the mc, vc, and the physical constant and the. Let me do the derivation also. So we had the initial momentum before the collision. So the block is just held by this person. So this block do not have any kind of the momentum. So because the velocity is 0 for that. So it is only the cart is moving. So I'm going to write it P initial momentum. The initial momentum is I'm going to write like this. So mass of the cart into velocity of the cart plus in the x direction only. Everything is moving in the x direction. So it is for x direction only that we are solving. So the mass of the block, but the mass of the block into the velocity of the block is 0. So it is just come out to be mass into velocity. That one. In the same way, the final momentum in the x direction only. So that is now the mass has increased. So basically the mass is the mass of the cart plus mass of the block that is get increased because as they stick together, so we had to find out that means so the mass they combine together. So you will get this expression. Then you have the 6 by 5 mc final velocity as the conservation in the momentum. So the final momentum have to be in the x direction have to be equal to the final momentum in the X direction that have to be conserved. So let me conserve that. MC get cancel out. So it is 5 by 6 of the. So this is the expression that I will get that. Hopefully you understood that one. So till now, everything is seems to be fine to me. Thank you. Okay, till now what we discussed is, so conservation of the momentum, by applying the conservation of the momentum, we get the final velocity. So this is the final velocity as you put it the block on the cart. That is, after that we will get this is the velocity. Let's move to the next part of the question is. So the next part of the question is we have it, and this is the straight line because the momentum is conserved. And this part we just drive that one, the second part of that one. The third is the drive the expression for the change in the kinetic energy of the expression that we had to find it out. So the change in the kinetic energy is change in kinetic energy that we had to figure out. So the delta K, that is the final kinetic energy, basically final mass. Let me put it the capital M, and the final velocity square minus initial mass. Uh, in, Initial mass that we have it, and the initial velocity that we have. So this is the expression for the change in the kinetic energy where the capital M is the total mass. After that you put it over there. So the total mass is, initially we have so the capital M is the mass, that the mass of the cart, plus you put the 1 by 6 of that. The total combined become total 1 by 5 of that. So this is 6 by MC. So that is come out to be, that is 1 by 2, 6 by 5, 6 by 5. But the expression that we get it, MC, and the final velocity that the expression is that we get it 5 by 6 of VC square of that minus half the initial, that the mass that is moving, due to that we have the kinetic energy is only the, so the MC V. So this is the expression that you get that, then it is half MCVC square, and that is nothing but minus 1 by 6 on that one. After that you will get minus 1 by 12 MCVC square. This is the change in the kinetic energy. The minus sign is just telling you the loss of the kinetic energy. The kinetic energy get lost into that. So this is the third part, the derivation for the change in the kinetic energy that we have it. The next one is, consider the case where the new block is dropped and the collide with the top of the cart. The new block slide along the cart during the collision, but does not slide off the cart. The time interval from where the new block collide with the cart and move together with the cart in the delta t time, where the delta t is that the fractional force between the new block and the cart. So you put for the delta t duration, so it goes with that one only. So the question is, now they are asking whether the x component of the momentum of the new block of the system increases, decreases, or remain the same. Because when you put, so just now you have to analyze this one. So when you have this block, now the first thing is you are putting the block in the y direction. So it gets stick together. So at now we had to be look into that because the momentum is only conserved when there is no external force. Now we had to be take the system. So what the system that we are studying right now? We are studying the system as a block and the card. So all the forces that are acting between the block and the card, that is considered to be internal forces. So there is no such external forces that result in the change in the momentum of the system is. So there is no change in the momentum. So the momentum remain the same. So the answer for this question is, so you have to simply say there is no external force that is acting over there. So it is going to be remain the same because there is no external force. External force that is acting on the system is 0. The force that is acting between the block and the card, that is considered to be internal force. Thank you.